Next question is, what is the difference between .py and .pyc? So in order to understand this question, we have to step back a little bit. So there are two types of programming languages out there as a general rule. There are compiled languages and there are interpreted languages. So remember that what we write as programmers is not directly run on the computer. You could write what's known as machine code, but no one really does that nowadays. I mean, unless you're taking a course or you're really a low-level programmer dealing with a small computer, the odds are staggeringly low that you're going to want to do that. So we write in a higher level language, and that higher level language somehow needs to be translated into the lower level machine code. So how does that happen? So in a compiler, what happens is the code is all translated at once, meaning code is translated once, turned into machine code, right, and then executed multiple times. You can think of this as reading a book or watching a movie in translation. Right? So let's say you're reading the book in translation. The translation is obviously wrong or weird. We've all seen all sorts of funny things on the internet where the translations were just incorrect or bizarre or, well, anyway. So there's no way you can go back and correct it or change it. You have a finished product. And going back and sort of comparing the original version, the source, if you will, with the compiled version is not necessarily going to be so easy. And in the same way, a compiled language can often be difficult to debug because what you have executing and what was actually originally written aren't necessarily correlated, obviously. I mean, they're clearly correlated. Should be a one-to-one correspondence there. But modern compilers do all sorts of optimizations and smart things and taking advantage of chips so that it might not be obvious where the problem is in the original source code. But at the same time, because they're dealing with all the code all at once, compilers can really optimize code and squeeze all the inefficiency out of it and even rewrite it. So that often compiled code is faster and better than a person could have done because the compiler is so smart doing that. So a different way of doing it is an interpreter. An interpreter translates the code into machine code. Let's translate the source code into machine code, line by line, each time the program is run. So the good news there is that you have this very tight correlation between what's written and what's executed. It's sort of like attending a lecture and hearing simultaneous translation. They speak, you hear the translation. They speak, you hear the translation. On and on like that, and it works really well. And if you're really lucky and you're in a small audience, you can ask the translator, hey, what was that? Can you explain that a little better? Or I didn't understand that. Sometimes translators will ask if something didn't make sense. And the same way in an interpreted language, if you're running it that way and you encounter a problem, because you have this tight correlation between the source and the machine code, source and the object code, you can really mess around with it. But because it's only doing it line by line, because it's doing it every time the program executes, you lose a lot of the efficiency. So typically, traditionally, compiled languages have been seen as harder to use, but faster to execute. And interpreted languages are seen as easier to use, but slower to execute. Enter the third type of programming language, which is byte compiled. And this is a hybrid. So the source code is translated, let's even say compiled, once into byte codes. And byte codes are basically, a high-level language, optimized. So it's a high-level language that can be interpreted easily and quickly. So which languages are byte compiled nowadays? The most famous ones for sure are Java and the family of .NET languages like C#. And in those languages, you compile your code into byte codes, and then the byte codes are executed by an interpreter. But that interpreter is highly optimized to work with those byte codes, and the compiler has done a lot of the work already of squeezing out the inefficiencies. Well, guess what? There's another language that works this way, and that's Python. We don't talk about a Python virtual machine, but it does actually work this way. Every time you write a program in Python, the program is first turned into byte codes, and then those byte codes are actually executed. Now, Python's compiler does not try to optimize for things. So if you write something really slowly and poorly, it will be slow and bad when it's actually executing. There's a very clear one-to-one correspondence between what you write in the source code and the byte codes that follow. And the byte codes are very high level as well, so you'll have things like start a loop and get an iterator and that sort of thing. But Python's bytecodes work pretty well. Okay, what does it have to do with .py and .pyc? So if I have a module and I import the module, should Python need to go through my module each time and compile it into bytecodes? No, that would be a real waste of time. So the first time that I import a module, the module is turned into bytecodes. Those bytecodes are stored to disk. And then the next time I import the same module, Python notices the pyc file and loads that. Let's see a quick example. So I've got here my editor. I've got Emacs. I'm going to say here x equals 100 and def hello name return hello name. All right, this is not the most exciting module in the world. In fact, you could argue this is the least exciting module in the world, but it is in my current directory. Right? So if I now say, let's do a mymod star, we see that there's one file here, that's mymod.py, and you'll see the backup file here as well, mymod.py tilde, but we really only care about the .py. This is my source code. This is what I'm executing. This is what I'm editing. This is what I'm working on. Fantastic. So now I go here and I say, import mymod. And we ask, okay, where was mymod from? And Python tells us, oh yes, module mymod was loaded from blah, 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 .py. But is that really true? Is that really true? Let's take a closer look. Well, sure enough, mymod.py is the only thing out there that starts with mymod. But it turns out that there's another directory there, and that directory is dunder pycache. And dunder pycache is the place that all the compiled Python files, compiled Python modules are stored in. And you can see here under dunder pycache, let me make this a little wider so you can see it more easily. Dunder pycache, we have a file called mymod.cpython37.pyc, meaning this is the pyc, the compiled Python. These are the bytecodes for mymod, as written by CPython, meaning the version of Python that most people use, written in C, version 3.7. If I were to load this module with a different version of Python, if I were to import with a different version of Python, then I would actually get a different pyc. For example, if I were to use pypy with it, let's see if I can do that. I'll just say here pypy3 minus mymod. I think this will work. All right, and now if I look here, what do you know? Now I have two different files. I have mymod cpython 37pyc and mymod pypy372pyc. So how does this work? All right, it's actually, it's a little complex, but it's not too hard to understand. Basically, Python tries to be smart about importing modules. So if there is a .py, but no .pyc, Python creates the pyc and then loads the .pyc. Now, why would it want to load the .pyc? Because it's faster to do so. The bytecodes don't require parsing. They don't require, we don't have to get rid of comments. We don't have to make sure the syntax is correct. It just goes through the bytecodes and reads them really quickly. So it's to Python's advantage to read the pyc. If there is a .pyc, but no py, Python loads the .pyc. And we'll get back to this point in a moment. Here's where things get trickier. If there is a py and a .pyc, and the .pyc is newer, then the .pyc is loaded. Meaning, let's say I've got both a .py and a .pyc in the same directory. Pyc is under pycache, of course. And it turns out that the pyc is newer than the .py. Well, that's what we would expect, right? I write the code in .py, I load it using Python, the .pyc is created automatically. So yeah, actually the pyc should be newer. So the pyc is loaded, all is good. But if there is a .py and a .pyc, and the .py is newer, then Python removes the .pyc and recompiles the module, creating a new .pyc, which is then loaded. All right, so you don't have to worry about compiling your code. You don't have to worry about the versions of this. Python does assume that timestamps on your system are going to work correctly. So make sure that your system is hooked up correctly to a clock or to a clock server like an NTP server. Otherwise, you might be in trouble. But this is all transparent. When you say import mymod, you don't know if it's from mymod.py, mymod.pyc, and so forth. Of course, I can check it, right? So I can say here, for example, I'll do import lib. And I can say import lib reload of mymod. There we go. No, it's still saying that it's using the, let's see, can we check if it's doing the pyc? No, it's still going to claim that it's using the .py there, even though I'm sure that it loaded the .pyc. One last point about these .pyc files. All the time people say to me, aha, it's compiled. So what we can do is we can ship the .pyc to our customers, thus keeping our source code safe. No, you can't. I mean, you can send them the .pyc and your code will work just fine. But because of the close one-to-one correlation between Python code and Python bytecodes, they can easily decompile your code from Python bytecodes, from a .pyc, back into Python, and it will look exactly like you wrote it, minus your comments. So really, there's no good reason to just ship someone .pyc. You're not really hiding the code from them in any way, shape, or form that's to be taken seriously. All right, so now you understand .py and .pyc and why they're both important and why, truth be told, day to day, you don't need to worry about it, even though it makes Python better and faster.